In a previous video, we looked at Bloch's theorem, and Bloch's theorem told us that if we're looking at solutions to Maxwell's equations in periodic media, and we write that down in a 1D periodic case, that if you look at the fields at a certain position z, and then you want to figure out what the relationship is between the fields at the position z and the fields one period away at z plus a, well, then Bloch's theorem basically told us that the relationship between these two fields is just a simple phase vector exponential minus j kz a. And then we've chosen to label our solutions, our Bloch modes, with this kz value here, this wave vector, as a label. Now, if you think about this for a while, you can convince yourself of the fact that this kz value is really only defined up to integer multiples of 2 pi over a. So pause the video and really try to convince yourself of this fact. So indeed, what happens in our Bloch mode formula here, if we replace kz by kz plus 2 pi over a, for example, or any integer multiple of 2 pi over a, then for this phase vector we get exponential minus j, and then we have kz plus integer multiples of 2 pi over a times a, and that just gives us exponential minus j kz a times exponential minus j, and then we have m 2 pi over a divided by a. So this basically is exponential minus j, an integer multiple of 2 pi, so this is just 1, and then we end up back where we started, exponential minus j kz times a. So actually it doesn't really matter whether you pick a certain kz value or whether you add any multiple of 2 pi over a to that value. So this means that a Bloch mode really is not characterized by a single value of kz, but actually by a whole family of kz values that are all 2 pi over a apart, at least in the one-dimensional case. So this in fact means that there's lots of redundant information if you plot, for example, a band diagram omega versus k. Again, because k is only defined up to an integer multiple of 2 pi over a. That means that just enough if you look at a zone which has length 2 pi over a, and then the rest will repeat periodically because of this mathematical property that we discussed here. And then conventionally, people choose the region minus pi over a plus pi over a as the so-called non-redundant zone of information for the k values in the dispersion diagram. And this zone they call the Brillouin zone. So that's the region of non-redundant information in the dispersion diagram. So if you plot, for example, the solutions and they look something like this, then the periodicity that we've discussed earlier just means that outside of this Brillouin zone, this pattern just periodically repeats, because you can add 2 pi over a to the k values as many times as you like, and nothing will fundamentally change with respect to the Bloch mode itself. Okay, so that's a very important realization for our Bloch modes. And again, this periodicity fundamentally comes from the fact that when we were looking here at Bloch's theorem, that we've chosen to label the modes not by the full eigenvalue, which would be this entire exponential, but rather we've chosen to label it by the kz value which appears inside the exponential. And that, of course, has as a consequence that this periodicity 2 pi over a appears.